we go. Okay, as I told you, make sure that you register our class on LMS because all the lecture notes and the recorded class URL will be on LMS. So you need to register our class there. And today we will start with the basics of numerical methods. And next week we will start doing the method solving part. Where is that one, I think. So you can see it, right? I will start the class. Let me see the messaging. You can write message if you have any question. Okay. Where we go? Where is that? So, as I told you, we will be talking about numerical methods for engineers. What does numerical methods means if you are asking that? So as an engineer, you will be dealing with most of the time nonlinear problems. So your problems will not be enough to solve with simple algebra, with pen and paper. So you will need the computer power to solve your problems. And to finding the exact problem for nonlinear questions, it's so hard. It's most of the time impossible. That's why we need some approach that we can get as close as possible to the real solution. And numerical methods are allowing this to us. So we are finding methods to the problems that we cannot solve exactly. And also, for example, most of the time you are going to be dealing with some experimental data. And you need to play with that data. You need to take the derivative of this data. You need to take integral of this data. So in short, if you want to do mathematics on a computer, you need numerical methods. And these methods, what we call it algorithms, that we need to write in a computer so that we can apply these methods. And in this course, we will be doing that. And since we are talking about approaching to the real solution, of course, our solutions will not be the exact, but we will go as true as possible. So since we are dealing with the numerical methods, we need to have some errors in our solutions. And at some part, we can accept these errors as long as it's not. So that's why, firstly, we need to talk about the errors and what kind of errors we can see when we are solving these numerical methods. So the first error is error in the initial model. The second one is truncation error, round-off error. These are very common errors you can come up. Error in the initial model is if you are assuming, for example, pi or e value instead of, or the gravitational, constant instead of the real one. If you are saying that, okay, I will take the pi 3.14, this is the error in the initial model. So you are saying that you are not getting the whole part of the decimal, you are just getting the 2 decimal parts. So this is an error. And quantifying this error is an easy way. You can quantify it by checking the absolute error, which is just the difference between the real one and the numeric one, and you are taking the absolute value. And the relative error, again, absolute error over the real value. So these are the easy way to quantify the first kind of error. Let's check that example. We have x, which is the real values 3, 14, 15, 92. But we said that it's so much, so I will just assume that this is 3.14. Then our absolute error will be x minus the real one minus the assumed one. And we are taking the absolute value for that, and this is the error. For the relative error, you are finding the percent of the error in a way. So it's much more trustful than the absolute error. If you look at the relative error for that one, we are dividing this absolute error to the real one, and we will get 0.05. So again, in 3 decimal place. And these are not so different for, between each other. So you can, trust any of it. But let's look at the B part. Here we have a value 1 million, and instead of 1 million, we will take this one as 9,900, 900,000, 999,996. Let's say it, that's easier way to say that. Let's assume like that. And to find the absolute error, you need to take the difference between these two numbers, and the difference is 4. You can think that, okay, this is a big error, but if you compare with the real one, which means that if you find the relative error, this will be, look at that, it is in 6th decimal place. So 10 to the 6 is a very good approximation for your numerical method or for your assumption. So this, you can trust the relative error in that part. And for example, for that one, what is that? The Z part, our real value is 0.00012. And the assumed value, or the one that we found as a numerical result, is that one, Z prime. And if you look at the absolute error, see that you can see that, okay, this is a very small error, so I can trust it, or I can use that numerical result. But once you look at the relative error, once you divide this one into the real value, and you will see that this is 25% error, and which is not less, and you cannot trust that numerical method. You need to, either check your experiment, or you need to check your method again, and you need to find a better way to approximate your solution. So relative error is much more trustful when you are looking for your result, and if you know the real result, you can compare with the relative error in a better sense. Okay. And another one is truncation error. By the way, you can stop me anytime and you can ask your questions. I am checking every now and then if you have any. Okay, it seems you will not. Let's see. Okay, and truncation error, how can we come up with a truncation error? These are some functions, and we want to define these functions: sine, cosine, exponential, power function. It is the root function. This is the logarithm function on a computer using only plus, minus, multiplication, and division, which means that I want to define this one in a polynomial way. So you know that the easiest way is defining as a summation of infinite series. So for any smooth function, I can define them in terms of the polynomial function. And once you have the polynomial function, you can easily work with the polynomial function than the others. You can take the derivative easily, you can take the integral easily, so it's much more easy as a computational power and as a normal way. That's why we prefer most of the time defining these functions in a polynomial way. But since this is an infinite series, you cannot take all these terms. You need to assume that, okay, I will take up to n term, and the remaining will be your error. And this is the truncation error that we are calling. And how to derive these series for a given function? Of course, the first way of doing things is the Taylor series. Let's remember the Taylor series. And after that, how good is our approximation if we only sum of n terms, and which means the truncation error we will be talking. This is the Taylor's theorem. You need to know that theorem. It's very useful, and you will be using lots of time in your studies. We have a function f, and we are assuming it's a smooth function, which means that its first n plus 1 derivatives are continuous. And f of x can be written, the sine function can be sine function, logarithm function, exponential function, any function you want. You can write this function as a polynomial in terms of its derivatives and not at x, at a, which means that if you are dealing with a function like exponential 0.0038, so since it is a very hard number to deal with, you can define this function as a polynomial function around 0, because 0.0038 is kind of close to 0, so you can open your function around 0 according to the Taylor's theorem. And the remaining term, the remainder term, we can write up to n, and after that the other term, since this is an infinite series, you can define this one as an integral form like that, or like this as a Lagrange form. And we will be using this Lagrange form a lot. This is much more easier to use. So you need to know this remainder term, because truncation error is, we can quantify the truncation error according to this remainder term. Okay. If I sum up for the Taylor series, it will provide us a mean approximate any smooth function is a polynomial, and also it will allow us to predict a function value at one point x in terms of the function and its derivatives at another point a. And we call this one Taylor series of f at a, or Taylor series of f about a. Okay, there are two ways to read that. And let's look at it on an example how we can write the Taylor series for e to the x. You know that the derivatives, what we need for the Taylor series, we need the derivative, first derivative, second derivative, third derivative, and x minus a square, and denominators are 2 factorial, 3 factorial, it's increasing like that. So first derivative, second derivative, all derivatives of e to the x is a to the x. So we don't have any problem to calculate that. And let's check it about 0. Let's take this Taylor series of e to the x at 0. So e to the zeros are all 1. That's why all our fk zeros will be 1. And we assumed a0. If we put it in the formula here, f0, f derivative 0, x minus 0, f second derivative 0, 2 factorial, x minus 0 square. So it will be going like that. And as you can see, since all the derivatives at 0 will be 1, we have only x here, we have only 1 here, we have only, again, x squared there, x cubed, x to the 4, it will go like that, and the denominators will be 1 factorial, 2 factorial, it will be increasing like that. So if you are opening, or if you are defining a Taylor series of any function at 0, this is what we call it Maclaurin series of f. And this is the Maclaurin series of e to the x. As you can see, instead of using the exponential function, you can use this polynomial function for your calculations. Or cosine at 0. The first derivative of cosine is minus sine, second derivative minus cosine, sine. So the sine will be always, positive, negative, negative, positive, positive, negative, negative. It will be like that. And at 0, the values of cosine will be always 1. The sine will be always 0. So if we write again in our Taylor series formula, you will see that this is going to be the Maclaurin series I'm calling, because we are looking at 0 again. So this is 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial. The sign is changing as plus to negatives, plus to minus in each term. So you can define as a summation as minus 1 to the n, because when n is 0, it will be plus, when n is 1 negative, when n is 2 positive. So when it is even, it's positive, when it is odd, it will be negative. And this will give us exactly this series opening. Okay. So make sure that you know how to write the Taylor series of any function. I will ask one question in your midterm about that. And here you go. This is the e to the x. We opened it as a Maclaurin series. But of course, we cannot consider all the terms. This is an infinite series. We need to consider the terms until n. And what is going to be the remainder term? This is the truncation error that we are talking about. Okay. This is the whole term is going to be the exact mathematical formulation. And we want to take the approximation for up to n term. and the last term will be the truncation error. And now we are gonna be asking how good is our approximation. If we only sum up n term, you can consider only 2 terms. Yeah, you can do that, but your error is gonna be much more higher. You can see that. You can consider up to 10 term. You know, it depends on that. But how can we quantify this error? We can do it by using the remainder term. And again, as a Lagrange, remember that this is our remainder. And this remainder is whatever you are taking as, it will be less than or equal to our remainder term. Okay? So this is how you can quantify the error in n term by checking the absolute value of your remainder in Lagrange form. This is the easiest way to quantify the truncation error. For example, for exponential function, it will be e to the x, n plus 1, x to the n plus 1, and n is depending on how many terms you are going to take. Let's look at this example. For example, instead of e to the 1, you can think that, okay, I will take only the, what is that, 8th term. Okay? So up till n equals 7, we will take it. So the bound of the truncation error will be e to the x, 7 plus 1, x to the 7 plus 1. This is going to be 8. So e is just, you know, 2 points, just a number. You can calculate that one. And you can see that your error bound will be less than or equal to 0.67 times 10 to the minus 4. So you can quantify your truncation error like that by using the remainder term. And let's look at it in a different way. If we want to approximate e to the 0.01 with an error less than 10 to the minus 12, at least how many terms are needed? So you want to get this tolerance. You want to get 10 to the minus 12 tolerance, and you want to approximate e to the 0.01. So yeah, your x is 0.01. You don't know how many terms you will get, but you want to know how many terms you will get to get the error less than 10 to the minus 12. So here, remainder term is that one. We know that this has to be less than 10 to the minus 12. And our x is e to the 0.01. I am just writing in the remainder term. E to the 0.01, n plus 1 factorial, 0 to the 0.1, n plus 1. And you can try for different n's. Of course, with hand, it will take some time. But for this one, it's not so much because you opened exponential around 0 and your value that you want to take for x is close to the 0. That's why you can reach easily after 5 steps, after 5 terms, you will see that your error is less than 10 to the minus 12. And I wrote a small MATLAB script here that you can check these calculations. You can do these calculations, and it's starting from 0, it's increasing 1, and I am just checking the remainder. E to the 0.01 over factorial n plus 1 times 0.01 to the n plus 1, exactly the remainder term. It is going to be calculating for n0, n1, n2, n3, n4, n5, n6. And you are going to be checking the results, and you will choose the one that is less than 10 to the minus 12 because you are looking for that tolerance, okay? Let's do it very quickly, just to take your attention in that way. Let me copy the one that I just wrote in here. And let me share with you. Where is that? Here you go, MATLAB. You can see the MATLAB, right? Hopefully you do. Here you go. This is the MATLAB. This is the command window. You can do any calculations. You can see as a calculator here. 2 plus 3. It will be giving you 5. You can say, what is the exponential 1? It will giving you, you know, the exponential 1 value. So this is like a calculator. Once you open the command window, you can do any your algebraic calculations in here. And we will talk about these, but right now, oops, I just write a small for loop that will be calculating us the remainder. And remainder we defined as e to the x over factorial n plus 1 times x to the n plus 1, right? So, and I defined it starting from 0 and it will increase 1 in each step until 6. So it will plug in 0 for n first and it will calculate the result. And then it will plug in 1 for n, it will calculate the result. 2 for n, it will calculate the result. And here 3, 4, 5. As you can see, this one is less than 10 to the minus 12. So you need at least 5 steps to be able to, at least 5 terms in your Taylor series if you want to get an error less than 10 to the minus 12. Okay? This is just a small script. You can copy paste from your slides and you will see the results in here. And let me share the slide now. Oh, what is that? No. That one. Okay. As we said, you understand that one, right? Why we need at least 5 terms. If you have question, please stop me and ask me. And let's do the same problem, but this time we will check e to the 0.5 instead of 0.01. Okay? We want to get e to the 0.5 by using the Taylor series, and I want to get 10 to the minus 12 error again. And now instead of 0.01, I am just plugged in 0.5 here, and we don't know, we are looking for x is 0.5. And once we do this and the same calculation, if you do it, you will see that you need at least 12 terms from the Taylor series expansion if you want 10 to the minus 12, less than 10 to the minus 12 error. So you need more terms. And why is that? Let's look at e to the, if you look at 10 to e to the 10.5, I want you to look at that one, please. I want you to try with a MATLAB, do the same thing for x e 10.5, check the error less than 10 to the minus 12, and you will see that you need at least 55 terms for that. How can we speed up this calculation? So in here you are trying to guess x 10.5, but you define your exponential Taylor series around 0. Since 0 and 10.5 has a big difference between them, that's why you need to get more and more terms to be able to get a better result. And if you look at the previous ones, for example, this is so close to the 0, that's why we need only 5 terms. And if we get a little bit far away than 0, now you need at least 12 terms. And if you assume x is 10.5, you need 55 terms. So in this one, either write your Taylor series around 10 instead of 0. You will see that you will get less terms to get that error. Okay. So a Taylor series converts rapidly near point of expansion. This is what I was trying to say, point of expansion. Since we expand our Taylor series around 0, if you are assuming your function far away than 0, you will need more and more terms to get. And this is just some showing. So more terms used implies better approximation. Of course, if you use more terms, you can get better approximation, or if you get smaller step size. And why do I call it step size? Let's check that one out. So before that, our Taylor series, we were taking h as x minus a, remember? So if we call x minus a h, this is what we call step size. And to make this step size smaller, we need to expand our Taylor series closer to the x. Okay? So when x is 0, when x is 0.01 and a is 0, this is small step size. But when x is 10.6 and a is 0, the step size is, big. That's why we call this one step size. And if you get a smaller step size, you will get better approximation for your Taylor series. And this is the truncation error. You need to know this remainder term because this is how we are calculating the truncation error. You need to know how to define a Taylor series for any smooth function around the given point. These are the points that you need to know for that part of the class, okay? And another error is round-off error. This is something you are familiar. So, for example, for p, again pi, check that out. This is p value, sorry. And for this one, you can get the round. You can round this number in how many? In 6 decimals, or you can chop that number in 6 decimals. If you are rounding that, since after 7 is coming, you can think this one as a 6. You are rounding up to one higher number. You already know that. And if you are doing the chopping algorithm, you can just chop it out. It doesn't matter the next number. Okay. And if you do that, you will have some error, and the error is again the difference between the real value and the approximate value. You can define the absolute error and define the relative error for the round-off errors in that way, okay? And now I will talk about little bit about MATLAB. This was the error part that you need to know. I will assign you a couple questions this weekend for you to solve. We did not talk about the syllabus, but I already shared with you. That's why I thought you checked the syllabus before. Did you check the syllabus before? Yeah, online courses are really hard. I don't know if you are following the course or not. Yes, great. I got one answer. Okay, great. So there will be, okay, great. Now let me try to open that one. Great. Here you go. This one. Okay, so next class we will do all root finding, Newton-Raphson, bisection, secant, regular falsi. So next Monday we are gonna be finishing that one, and after that you have your first kind of quiz there. Okay, I will be giving examples and I will be giving you the quiz. And some of the quizzes I can give you take home. Some of the quizzes it will be, it will be all take home, but in a hour. You need to turn it back in an hour. Okay, something like this. Any question? Okay. So, and I just want to show it here. There will be some homeworks. These are 10%. And quizzes, since there will be 4 quizzes, I will not give so much homework, but these homeworks can give you an idea about the quiz problems. And during the course, also, I am telling you, I will ask one question about that, which means that I will ask for sure. Make sure that note these questions also. Okay. And final will be 50%. And these are the quiz dates. And hopefully there will be no problem and we can apply our quizzes on those dates. Now, I want to show a couple, the introduction to MATLAB part in here. Any question about the course? No, okay. Now I will stop sharing that and I will share the MATLAB with you. CLC command is gonna clear the console, means that it will clear what you wrote so far. Let me close those, we don't need that. Let me close that one too. Okay, this is your console and we will be dealing with console and we will be dealing with the script programming. And script one, we will be coming to the next week. You can write your formulas and things in here. You can save that and you can run that. Okay, but for the command window, you don't need to save it. You can just press enter and you can see the solution directly. So what kind of things we are doing that? For example, we can define a vector. Since we are going to be dealing with data, we will be dealing with vectors a lot. For example, let me define a vector. V equals, to be able to define a vector, you need to use square bracket, open and close, and 0, 1, 2, 3. Okay, this is a row vector. So if I say enter here, it will give me, it will assign V into a row vector, 0, 1, 2, 3 elements. Okay, this is 1 by 4 vector. You can see that. If you want a column vector, you need to define, let me call it, instead of V, let me say column vector C. Between them, if you put semicolons, your vector will be a column vector right now. Okay, or you can take the transpose. This is also, you can see that, you know, C2 equals V transpose. You know transpose from the linear algebra. Getting transpose means that you will turn your row into columns, columns into rows. So C2 again, the transpose of V, which will be 0, 1, 2, 3 as a column vector. Okay, and you can access any entry in a vector. For example, you can see that I want you, of course, once you have a data, you will load the data in the MATLAB, and this will be maybe 100, maybe thousands of values there. So you want to access any value by just calling that. You can say that I want to see the third value in C2. And it will tell you, oh, 1, 2, 3, third value is 2. Okay? So you can access any entry in a vector by just calling it in an order. Or you can change that value. So you saw that, okay, this shouldn't be 2. Oh, I made a mistake. This should be, C2 should be, sorry, C2, 3 should be, I don't know, 45. And now it changed the 2 with 45. Because I told them that change the third entry in C2 with 45. Okay, this is what you can do. You can extract a slice out of a vector, which means that you can see that I want to see the entries from 1 to 3 in C2. So it will give you first entry, second entry, third entry. This means that this colon means that 1 to 3. This is the starting and this is the ending value. And all integers between them is counting. Okay. And also you can make vectors in an easier way. You can say that my x vector is gonna be between minus 10 to 2, and the increment for each is gonna be 1. So this will give you minus 10, minus 9, minus 8. So it will increase the minus 10 in with one step in each order. Look at that. Minus 10, minus 9, minus 8 until it will go to 2. Okay. So this is the starting point. This is the last point of your vector and this is the increment. You can play with that. So you can write that instead of 1, you can increase in each step 2. So it will be minus 10, minus 8, minus 6. Okay, make sure that you understand and you play with that. It's very useful. You can use a lot in your work. Or you can define the vector with the linspace command. I already shared the notes with you. You can say that between 0 and 1 divided into 11 parts. So it will divide by itself. You are not, telling the increment. You are just saying that I want that much, division. And it will divide 0 to 1 into 11 points, and it will give you the vector like that. So any question about vectors? You can define a matrix. So row by row. I say that my A matrix is 2, 4, 6, 8. And I am going to the second row. This is my first row. It is 5, 8, 2, 12. I don't know. I'm just writing something. 7, 9, 0, 0. Okay, this is 3 by 4 vector. Okay. And you can again call any entry. You can say that second row, third entry, third column. Give me second row, third column. This is the entry 2. Okay. You can call give me the first row. Okay, fourth entry. First row, fourth column. 8. First row, fourth column. It's 8. Okay. Again, you can change that one. You can say that this is equals to 23. It will change this 8 with 23. So you can do these vector operations and matrix operations easily in MATLAB. Any questions so far? You did not understand the linspace command? Sure. So linspace, you are just giving the first and the last value, 0 and 1, and you say that put 11 elements between 0 and 1. So, and it will make 1 minus 0 over 11 minus 1 and minus 1. This is what it is doing. B minus A over C minus 1. Okay. You can try with different values so that you can understand what it is doing. For example, 100 and 100, let's say 21. See, 100 over 20, it will be 5, so it will be, the increment will be 5 in this case. B minus A over C minus 1. Okay. Buse, is it clear? Barış? It's not clear? Let me see. Okay, great. So these are how you can define vectors. And what else? So plotting the data one. Let's see that you did some experiment, or some experiment is, you took from some group an experiment, and you need to, firstly, the first thing you can do, and this is the most useful thing and the easiest thing in the data, is plotting that one. How does it look like? It is the easiest thing that you can do. So I already shared with you. Now let me share one more time. It's gonna be better, I think, for you to see it. Let me stop sharing this one. I want to share the lecture notes because I want to show you. Here you go. This one. Let's say you have a data, which means that the temperature over the viscosity. So whatever you have as a you are increasing the degree of some material, and you are checking the viscosity of that. And when this is 5 degrees, the viscosity is 0.08, some liquid you have. And when it's 20 degree, the viscosity is 0.015. So it is like it is increasing little bit and decreasing and decreasing and decreasing again, something like this with degree. But of course, this is just 5 data points, so you can see it. But for the bigger ones, again, you need to see the general form of the behavior to be able to do that. Let's plot that one, okay? So what I want to put the temperature degrees on x-axis and the viscosity values on y-axis, okay? Let's put them. To be able to do that, we need to define these temperature and the viscosity in a vector. Let's do that. Temperature vector I am opening. My temperature vector, again, how we were defining the vector, with square brackets, 5, 20, 30, I am defining as a row vector, 50 and 55. It was given to me. And one more thing. So since you already know, you don't want to see the result of this row vector because you know what you will see. And if you don't want to see the result, if you don't want to have a mess in your codes, in your calculations, you can put semicolon at the end of your script and you will see that it is still t is assigned to this vector, but it does not show the output to you. Okay? If you want to hide the output, you can put semicolon. If you clear the semicolon, it will show you the output. Okay? So semicolon is very useful in your codes most of the time. So T, mu viscosity, values. Again, I'm defining 0.08. What else? 0.015, 0.009, and you don't even write 0. You can put, instead of 0, just point, by the way. This is also on another thing, but I don't want to confuse you. You can just put it there. And again, I'm putting semicolon. I don't want to see the result because I already know that. Let me see. This is 1, 2, 3, 4, 5. 1, 2, 3, 4. So I miss one value. If I do that, if the sizes does not match, I cannot plot it. So here you go. I define t and mu vectors. By the way, you can easily check the size by size command. You can say that size t is 1 to 5 vector, and again size mu is 1 to 5 vector. So the sizes are okay. So I can easily plot them. Size plot command. So for the first one, I want to put it on the x-axis. So I want to put temperature in the x-axis, and I want to put the viscosity values on the y-axis. If you do that, plot T mu, it will plot it. Here you go. Okay. And it just 0.08, 0.015, 0.09. So it's decreasing, as you can see, right? Why did I say increasing in the middle? Okay, it's decreasing. That's good. And since you cannot see the data points correctly, to be able to do that, you can specify that for my data points, put circles. Now let's check. Now you can see the circles, right? Instead of the line. And you can even put a line. If you say put circles and line, it will put circles on the data values. It will be connected with a line between that. Okay. There are different plotting options for MATLAB. You can write help plot and it will give you all the details about plotting. So you can say that plot with color blue. Sorry, it was blue. Let's make it red. Red is R. So now my line is... Oh, you cannot see the graph? Sorry. Okay, sorry. Now let me... Maybe I can share desktop. Desktop. Let me share desktop. It will be easier. Now, do you see the Plotting figure. Can you see the figure?
Yes, teacher.
Yes, great. Okay, great. Now let me go over. So firstly, we just plot t and mu, and this is what we saw. So just a line, it is connected with a line. Okay, but I wanted to specify the data points. That's why I put circle. And once I do that, it just put a circle there. Now it's hard to see that. I want to put a circle and a line. And to do that, I just put circle and line here. And it just puts circles for the data and the line there. And to be able to change the color, you can specify the color there. You can say magenta. You know, it's like pinkish, purplish color. Like that. You can change, instead of circle, you can say, I want to put star. Okay? So it will put a star for the data. So these are just, you know, some properties for plotting. And to see all those, you can see help plot, MATLAB, sorry, plot. If you do that, you just wait a little bit and it will show you all, for example, the color ones. For blue B, green G, red R, for point, circle, star, and to the lines you can do solid, dotted, dash dot, dashed. Okay, you can specify all those plotting options by checking help plot. Okay, and let's do it like dashed, magenta. You can even say here, if I remember it, like right line width, and you can say that 2. So you can increase the width of your line. See? Okay. If you make it 3, it's gonna be much more bigger. I'm just playing to show you. And let's make it circle or dash. What we can do it more. I don't know. What was that? Let's check it from here. Diamond, D. Let's make it diamond, D. See, put diamonds here, but now line is so width. So you can specify all those in your plot. And now this is good. Yeah, you can plot it. Specify your plot. They can understand what did you plot. Okay. So you can add labels. X label. And what was the temperature? It did temperature here. See? And you can put Y label. And this was viscosity, right? No, in the Y label, it says viscosity. And you can put title. I will ask you to put title in an exam and in your homeworks. Your name. Let me write my name as a title. Or you can say that the, you know, in general, the experimental results. I don't know, you can specify your title according to your work. So it put it in here. And if you have more than 2 viscosity values, for example, for the same temperature, so I defined T and mu. Let's say in the first experiment, you find the viscosities like that. And for a different pH value, for example, you did another experiment and you found the values like that. 5, 0.0, 23, 0.008, 0.003, 0.0001. Let's say. This is your second mu2. And you want to plot both experiments in the same window. Okay. So we had this plot window. By the way, if you press to the up arrow in your computer, it will show you what did you write before. So you can call easily what you did, what you wrote before, and you can, change that one. So first I plot temperature versus mu, and these were the specifications of my line. And now let's make this one is the first line. I want to add the second experiment in the same window. Y vector, check that out. That's why I write my X will be the same temperature, my Y will be the mu2, and I specify for the second lines, I will say cyan and what is that? Okay, circle, doesn't matter, and let's make it that. Okay. Once I say enter, see it added the second temperature results here. And now you want to specify which experiment is about which one, and you can do legend for that. You can add legend. You can say that the first plot I defined was the first experiment. I don't know, you can say that pH something like this, or first experiment, let's write. And you can say that the second experiment I did is the second plot I defined. If you do that, it will add the legend. It says that the first purple line is belong to the first experiment. The blue line is belong to the second experiment. Okay. And since I did not define X label, Y label, you can define it again here. Viscosity. I don't know. Let's make it the whole title. And that's it, I think. See, X label, Y label, title, legend, and my plus are here. Okay. Any question about plotting? Plotting is very good for you. Whatever you have, we will be defining functions. We will plot the functions in the next class. But right now, if you have a data, you can easily define them as vectors and you can plot them. Okay. There will be one plotting question in your homework I will give also, and also I will give you in the your first quiz. Any question? Okay. What else we have? Okay, there are some built-in functions in MATLAB, so you don't have to define sine, cosine, exponential there, because it's already defined in the MATLAB. So you can look at sine pi, it's already there, it will give you the result. Or cosine 0, which will be 1. Or, exponential function, exponential 0, which is 1. So these are built-in functions, and you can check built-in functions in MATLAB. You can see all the list of the built-in functions: cosine, tangent, hyperbolic sinus, hyperbolic cosinus, logarithm. These are all, by the way, log is the ln function. Log10 is the normal log in MATLAB. Inverse of sine, inverse of cosine. These are all defined already in MATLAB. You can check, you can Google it and check it easily, built-in functions in MATLAB. And what else we have? And let me do just one example here. Let's say that X is from 0 to 2 pi. And the increment is 0.05. I don't want to see the result because the output will be something messy. I don't want to see that. And I want to define my sine function, sine of X. And all those x values that I defined, it will be put it inside the function, and it will be another vector here. Okay? And I don't want to see the result again because it will be a bunch of numbers. But I want to see how it behaves. So I can just plot x, comma, y, make it red line. Okay? And it will show you the sine function from 0 to 2 pi with an increment 0.05. I want to show you something else. Let's say I will define another x, let me say x1, but the increment will be 0.5. So I increase the increment. Okay, let me call y, define a different way, and let's plot it. x1, y1, I am plotting it this time. Let me plot this one. Let's say hold on. If you say hold on, whatever you plot, it will be plotting over the same window. If you don't say plot, this window is gonna be deleted and the new plot is gonna come. Okay, that's why I am putting the hold on here, and let me put in a blue line there, so that I can see both of these figures. Check that out. This blue is when the increment is so big. This red is when the increment is small. So what I wanted to show you here, if your increment is not small enough, you will not get a smooth function. Okay? If you want to get a smooth function, you need to get your increment. You need to get as much point as possible between your starting and ending point. Okay? This is just to show you it is important for you how to define your increment. It should be small enough. If you get so small, of course, it will take some time to do that. These are easy calculations. These are not maybe, but for your other calculations, it can take some time. But for the smoothness part, to get all information you want, you need to get a small increment. Okay? And I want to show you how to define a function in MATLAB. One way to define this one is an inline command. With an inline command, you can define a function. Okay, f equals inline. Now I will define 2 times x squared minus 3 times x plus 5, let's say. Okay, and I'm saying that my independent variable is x. So it makes f, it defines the function x in here. And you can call f of 5. What it will do, it will plug in 5 for x. There is no problem. But if you define your x, as a vector, let's say minus 2 to 2, the increment is 0.5. If you do that, if you define this one, and if you want to, put this vector inside your function, if you call f of x, it will give you an error. Why? Because what you are doing in here, you define x as a vector, and in this one, for example, x squared means that multiply x with x. So you are trying to multiply row vector with a row vector. And you know that from the linear algebra, you cannot do that. The sizes does not match. So that's why it gives you an error. But what you want to do exactly is you want to put these element-wise. You want to plug the minus 2 first, then minus 1.5, then minus 1 inside that. But since you define this one as a vector, it just put this one inside as a vector. So to make sure that you want to do element-wise multiplication, once you are defining your inline function, you need to put dots before the algebras that can. For example, x squared is going to make a problem. You cannot multiply one vector with another as long as the sizes does not match. 3 times x does not give a problem. 5 does not give a problem. But if you think that the element-wise calculations you need to put a dot before the sign of your calculation. Before the square, before the multiplication, before the division, put dots. This is so important. Okay. Now this is your f function. Now let me call f of x. See, it's calculated because now it is just plug in one by one in each element in this vector. It does not take this one as a whole vector. Okay, this is the difference, and it's important for you once you are defining your functions. Don't forget to put dots before roots, before powers, multiplications, and divisions. These three algebraic formulations, you need to put dot before that. And now you can even plot that one. Plot x versus f of x. Make it yellow. You can see hardly, but let me make it yellow. Doesn't matter. Just for you to see that. See, since I put hold on, it just plotted over the opened figure. If I close that figure and if I call it again, it will plot it by itself. Okay. This is the f of x function when x is between -2 and 2. So you can easily observe these functions with MATLAB. Do you have a question? As I told you, next week we will cover all root finding methods, Newton-Raphson, bisection, secant, and regular falsi. And so that in the other week we can have our first small quiz, and I will share with you some homework kind of problems in this weekend. Right now I will finish the class, but before that I want to get, how can I was taking, I knew how was here, was it here? Hocam, where will you upload this recording? I will, the link I will attach to the LMS system. Okay. There you go. I will download the attendance list. Hopefully I did. What is that? Another question? Let me check. There you go. Okay, I will send you the link, okay? Faize. Yeah, that's right. I did not open from the thing because I wanted to make sure everyone got this invitation. I could not download the attendance list. I don't know why. Anyways, doesn't matter for the first week. Any question? I think that will be it for today. If you will have a question, you can ask me with an email. Okay, Onur. We will continue like this next week. We did not have any problem according to the connection, it seems. So if you will have suggestions, you can always share with me. Okay. Okay then. See you next week. Make sure that follow our class from LMS and mail group. I will be sharing all the updates there. Bye.